Hey everybody, welcome back. Today we have the first video of an additional new series we're going to do where I've been saying I'm going to code up a Hartree Fock program. So we're going to get started today. This is going to be sort of a lengthy video and a lengthy series. It's going to take a lot of time between videos, and each video is going to be pretty long, maybe 30-40 minutes, although I don't know how long this is going to take. But yeah, we're going to code up a Hartree Fock program in Python. Here I have the Anaconda Python downloaded here through this Anaconda Navigator. So you can easily just Google Anaconda Navigator, download it, and start using this on your desktop. It's very straightforward to do. I also have the basis set exchange open here. You literally just Google basis set exchange and it'll bring you here. And what we're going to do today is we're going to start building our Hartree Fock program. So this is the Jupyter Notebook thing here, and I guess you'll also learn how to use this through the course. So I'm just going to go ahead and make this first cell a markdown, and so let's call this Hartree Fock program v1 because it's our first file. We'll update this every time. And so here are the Hartree Fock equations. You have the Fock operator acting on your coefficient matrix. The rows of the coefficient matrix are your atomic orbitals and the columns are the molecular orbitals. And this equals the energy eigenvalues of your system times an overlap matrix times the coefficients. And this overlap matrix is what we're going to be computing today. And then in subsequent videos, we're going to make the Fock matrix. Now this Fock matrix is going to have the, electron kinetic energy, the nuclear electron repulsion, and then it's also going to have the electron-electron repulsion. We will do these in future videos, but today we are going to do the overlap matrix. So this is equal to the overlap matrix, and the rows and columns here are going to be our basis functions, and the basis functions are in a Gaussian basis set. They're basically just a series of primitive Gaussian functions. So without further ado, let's get started. So we're going to need a few things. I'm going to import system because sometimes we might need to put up a sys.exit to debug the code. And also going to import NumPy. Import NumPy as MP. Okay, so I'll be able to use this as well. And I also save constantly. So let's go ahead and run this. That's it. Okay, so this star means it's running. It kind of takes a while the first time it's to run. So here's basically what it is. So a lot of people, they're confused, like what exactly are our molecules? And how I'm going to do it here is I'm going to code this Hartree Fock program not in a way that might be the best for speed and computation, but in a way that's, it's going to teach everybody what they need to know. So I just want to put this disclaimer out there. It's not to be the best Hartree Fock program on the planet, but it is supposed to be in a way that is very illustrative of what's going on. So what we're going to do is we're going to first do this for an H2 molecule. So it's 2 nuclei. I feel like this is better than a helium atom because a helium atom is only 1 nuclei. And the program is a little more challenging and it's more conceptually gratifying if we have 2 nuclei. Because if it's just one atom, then it's kind of hard to see how this works in a many nuclei case. So we'll do H2, so it's only going to be s orbitals. Then what we'll do is we'll do H2O. We're going to do water. So our first order of business is we're going to do the H2 molecule, and then we're going to do H2O. The reason why we're going to do H2O is because it has p orbitals from oxygen, and the Gaussian basis functions are much, much more complicated when you have angular momentum terms. And basically I want to show you guys how you would do that with an angular momentum. So the math is much simpler when you only have s orbitals, but I want to show you guys how to do it with p orbitals as well. And then d orbitals, f orbitals, these are much easier once you know how to do the p orbitals. Okay, so what we're going to do is we're going to basically have this thing called molecule. Okay, and our molecule, our H2 molecule, is going to be the H1, so the first hydrogen, and then it's going to be the 1s orbital on the first hydrogen, and then it's going to be the 1s orbital on the second hydrogen. Okay, So literally our system is just two basis functions. Each basis function is centered on each hydrogen, and each basis function is just the 1s orbital. Now, when you express a 1s orbital, how are you going to do it? Well, you do it by using basis functions, right? And the question is, what basis function are you going to use? So here I'm at the basis set exchange. I'm going to be showing two basis functions today. I'm going to show the S31G basis set, and I'm also going to show the STO3G basis set. So we'll start with the STO3G basis set. So what I do is I click here, then I click hydrogen, and then I click get basis set. And here are the here are the alpha values and the contraction coefficients. So basically our 1s orbital here for hydrogen is a linear combination of three Gaussians. These are the alpha values in the Gaussians, and these are the coefficients in the linear combination. Okay, so what I'll do is I'm just going to exit out here for now, and I'm going to come back and get it when I need it. Basically, so now what we have to do is I'm going to define this H1, 1s. So our s orbital is going to be hydrogen 1, and I'll say primitive Gaussian 1. Then it's going to be, I'll actually say primitive Gaussian 1a. Then it's going to be hydrogen 1, primitive Gaussian 1b, and then hydrogen 1, primitive Gaussian 1c. Okay, so I haven't defined these yet. Okay, these have yet to be defined. I'm actually doing a really nice strategy called retrosynthetic analysis. I'm basically starting at my end, my molecule, and working backwards. I think this is a really intuitive way to teach, because most people, they kind of want to start at the beginning and move forward, but it's kind of easier to unravel things when you start at the end. So this is just this is the 1s orbital on our first hydrogen. And then what I'm going to do is make the 1s orbital on the second hydrogen, so we'll call this H2, and then I just turn all these to H2. Okay, so now I have some object right here. The 1s basis function on the first hydrogen is a list of three primitive Gaussians. Okay, so now what I need to do is I need to make these primitive Gaussians. And what I like to do here is I like to make a primitive Gaussian class. So basically what happens is I can access components of these primitive Gaussians later. So we just saw for the basis set, each primitive Gaussian should have this alpha values, a coefficient in the linear combination. We're going to make a class. So we'll call this class primitive Gaussian. Okay. By the way, my spelling is terrible, so this could be completely wrong. So it's a primitive Gaussian class. And each class in Python takes this init you can think of it as an initializer for the class. So it has this self value. Now what do we need for each primitive Gaussian? So each primitive Gaussian will have an alpha value. Okay. It will also have a contraction coefficient. So we have a linear combination of Gaussians. What is the coefficient in front of each Gaussian? That's its coefficient. It's also going to have coordinates. So these are the atomic centers of the Gaussian. And it's also going to have some angular momentum numbers. I'll call it L1, L2, L3. Now for an s orbital, these are all 0. So what we're going to actually do now is, because we only have s orbitals in our basis, we're going to just basically ignore these for this video. And maybe in the next video, or when we do H2O, these will become important. So what we have here is, I forget if I need one of these here. I guess I'll find out soon enough. So what I want to do is I want to access, so I'm going to say that self.alpha equals alpha. Okay, so this alpha here is basically going to be sort of initialized within the objects of the primitive Gaussian class. Then we're going to have self.coefficients here. Oops. Sort of coding this in real time, so I'm prone to make mistakes. This will be equal to coefficient, so coef here. And then self.coordinates is going to be equal to the coordinates that we initialize. And then I can go ahead and initialize these as well. I guess I'll do it. I'm actually just going to leave it. I'm not going to do these now, but we'll have to do these in a future video. And then we should also have the normalization constant. So I'll just put this as A. And for a primitive Gaussian function with no angular momentum, the normalization is actually going to be 2 times alpha, okay, over pi, which means I need to import math up here. So 2 alpha over pi, okay, and then raised to the 3/4. Now, if we had these L orbital or these angular momentum values in our Gaussian, there would be other terms here. So it'd be plus other terms for L1, L2, L3 greater than 0. Okay, so they're terms with L's in the numerator, basically. But for now, if you just have S orbitals, this is all it is. Okay? And then, yeah, so this is basically our primitive Gaussian class. Now let's go ahead and make a Gaussian. So what I'll do is our primitive Gaussian. So I'll set this up here, H1 PG1A, okay? So this is the primitive Gaussian 1A on H1. This is going to be equal to primitive Gaussian, and I'm going to have to go ahead and now basically set these things in here. So the alpha value, let's go back to our basis set exchange, STO3G basis, get basis. I'm just going to go ahead and copy these in one by one. So we're going to have this. And this, okay? So this is the first alpha, the first coefficient, and then the coordinates, I'm going to center this Gaussian on 0, okay? And then I'm just going to set these all to 0, so it's an s orbital. Okay, so this is our first primitive Gaussian on H1, and then I'm going to make the other two. At this point, it's just kind of straightforward. Now, the only thing that's going to change here are just these coefficients. So I'll come back here. Oops. So this one will go here. And then we have this one here, this alpha value. So I hope this is clearing some things up for everybody. It can be tough. This part here actually is very conceptually challenging, so that's why I thought we would just make a video and show all of this. So yeah, here I basically have just made the 1s orbital on the first hydrogen. So the 1s orbital on the first hydrogen is just a list of primitive Gaussian class objects. And each primitive Gaussian class object has its own alpha value, its own coefficients, its own coordinates. All of them are centered on the atom at 0. And it has the angular momentum value. Is it a p orbital, d orbital? Here they're all s orbitals, so these are all 0. And because these are all 0, we have this simplified expression for the normalization constant. Okay, so now let's go ahead and make the primitive Gaussians on H2. And so these are actually going to be exactly the same. The only difference is going to be the atomic position. So I'll make this at 1.2. So I just displace the hydrogen in the x direction. So I basically have a hydrogen atom in the center and then a hydrogen atom just shifted in the x. And the reason why these are all the same is because each hydrogen's 1s orbital is expressed in the STO3G basis. So this is STO3G basis for 1s orbital on hydrogen. When we do the 613G basis or 631G basis, yeah, 631G basis, we're going to have a 2s orbital. So that's a little more interesting. Anyways, so this is the STO3G basis for the 1s orbital on hydrogens. I basically take these H1s, put them in for the H1 1s. I take the H2, put them for the H2 1s. Then I combine these together and I make my molecule. So my molecule is a list of lists of primitive Gaussian class objects. So let's go through here and see all the bugs I have in my program. So I run this, invalid syntax. So I probably need one of these things here. And then I probably don't need one here. unexpected indent self here. I'm doing something wrong here. Init is not defined. Oh, definite. Ah, yes, that's what it is. Okay. Ah, yes, I forgot this def. It always throws me off when you have class and then def. Okay, anyways, so this is now working. It's just some simple debugging. And now here, let's run this to see if we can call these objects well. And it looks like we can call them fine. Let's go ahead and do a little test. So I'm just gonna, I have this H1P1 or PG1A and this dot alpha. Right, let's see what we get. 3.4. So right, we call this alpha. And then let's do this dot coefficient. All right, and maybe this dot A. Okay, so very nice. Let's now go ahead and write our function for the overlaps of the basis functions, okay? So let's press this plus here, and now we're going to do def overlap, okay? So this is going to take our molecule. So it takes our molecule, which is a lists of primitive Gaussian basis objects, and then it's going to basically overlap them. So the overlap matrix, recall up here, this overlap matrix in the Hartree-Fock equation, it is the number of rows and the number of columns are the number of basis functions. So here we have two basis functions, so this should be a 2 by 2 matrix for the H2. When we have more orbitals, like for the 631G basis, we're going to have, I think, maybe 4 rows and columns here, something like that. So now what I basically want to do is I want to call this overlap molecule, and I want to have it output the overlap matrix to be used in the Hartree-Fock equations. Okay, so it's going to be the overlap of our basis set, and we're going to do 2 basis sets here. So this is the STO3G basis set right now. So for this overlap function, so I need to first extract out the number of basis functions. So I'll call n basis, oh, if I could spell, n basis equals the length of molecule. Okay, so here it's just going to be 2, right? And then what I want to do is I want to make my overlap matrix. So I'll say S equals numpy dot zeros, and I'm just going to make it a basically a 2 by 2 matrix full of zeros. So n basis. Okay. And now what we need to do is we need to loop over each basis function. So what I'll do is I'll go for I in range n basis. So for each basis function, so you can think this is for basically each row in S. So now I'm at the first row in S. And now I have to do for each column in S. So for J in range n basis. Okay. Now here I have this H11S is 3 primitive Gaussians because I have the STO3G basis. But when I have a different basis, I might have 10 basis functions. I might have 6 basis functions. So I can't always just rely on the fact that there's going to be 3. So what I have to do is I have to basically extract how many primitive Gaussians are in each basis function. So I'll do it like this. I'm just copying this, so I don't have to retype it. N primitives in basis I equals, we'll have to do the length of molecule I. Okay, so molecule I will be where this index in this loop is here, and the number of primitives in molecule I is now equal to this. So I'm actually just going to make this n primitives I. Okay, and then of course we have to do the same thing for J. Okay, so it should be good so far. Let's just give it a save. And now what we have to do is we have to loop over each number of primitives. So we have I and J here. So we'll do for K in range n primitives I. Then we have to do the same thing for j. So I, j, k for L in range n primitives j. Okay, now we have to overlap the orbitals. Now recall we're only using s orbitals here, so the overlap function is greatly simplified. In the future videos, I'll be writing the full expressions for overlapping p orbitals with s orbitals, overlapping d orbitals with p orbitals. I guess for the H2O example, we'll only be sticking with p orbital overlaps. But basically what we're going to do is we'll have primitive Gaussian functions representing p orbital basis functions, and then we'll be overlapping the p orbital primitives, or the Gaussian primitives that make up the p orbital basis. So anyways, let me just recap what we're doing. We're overlapping the basis functions in molecule, so we loop through the basis functions, and then we realize, okay, these basis functions are just a bunch of primitive Gaussian class objects, so now we have to overlap the primitive Gaussian class objects. So how do you compute the overlap of a primitive Gaussian function? Well, you could do it in general using these angular momentum terms. It's very sort of in-depth. We'll do this in a future video. But for now, we're just going to do it. We're basically just going to use the radial parts of the Gaussian because we're assuming we're only using s orbitals. So we're just doing basis steps. Take one more sip of my tea. Okay. So now we are integrating two Gaussian functions, essentially. So let's go ahead and multiply their normalization constants. So this will be n, we'll call it. The normalization constant of the total overlap will be equal to, so this is for molecule I. So here we have molecule I, right? Molecule I is what? This H, the 1s orbital in H1. And then we're looping in this loop, so now we need to have some subindex for here. So we'll call this K, right? This is K. So molecule I dot K dot A, that's this one, times molecule, I think this will be JL, right? Okay, so there's a normalization constant in the overlap. Now, using the Gaussian product theorem, you can just Google this. You end up getting this set of auxiliary variables with the alpha coefficients. So basically, one of the reasons why Gaussian basis functions are used is because you can basically separate them into individual x, y, z components when you do the overlap. So if you were to basically do this three-dimensional overlap with Slater type orbitals, you have a square root term because you have this exponent to the r, e to the minus r, but the r is the square root of x squared plus y squared plus z squared, so you can't separate it with that square root term. So when you square r, like in a Gaussian function, you end up being able to separate it, and this allows you to basically use the Gaussian product theorem, and the Gaussian product theorem lets you map two center integrals onto a one center. And when you do this, though, you have these like new terms, p and q. You'll see I define here. You can read about this elsewhere. I'm just showing you sort of the computational implementation of this in the HartreeFock program sort of scope. Okay, so now P is going to be molecule. It's going to be just a summation of the alphas. So the alpha on the first primitive Gaussian, and so I have two primitive Gaussians I'm overlapping. So here's the alpha on one of the primitive Gaussians. Here's the alpha on another primitive Gaussian. So I'm just basically summing them here. And now I'm going to have this new variable Q, which is going to be the product of these. Oops. It's going to be this alpha times this alpha over P. Okay. And you also need this sort of distance between the two Gaussian centers. So that's actually going to be this coordinates here. So I'll do this molecule I K dot coordinates, and this will be minus JL dot coordinates. Okay. And then I want to square this. So one way I can square this is I can do numpy dot QQ. So I just take the dot product of these sort of two vectors here. Let's see if it doesn't, not going to let me do that. Maybe I can just, let me just try Q times Q for now. Okay, so this is this distance squared. I don't know if these, I don't have these as numpy arrays, so I don't know if I can use this numpy dot on them. So let's just do it like this for now. And now I basically have what I need to make the matrix element. So recall I'm loop, these are the loops for the matrix elements of S. So now I have Sij, okay. So here it's already a 0. So we're going to do this sort of, we could just set it equal here. So we're going to have it be the normalization. And then what we have to do is remember that we have two Gaussian primitives, so we're going to have to multiply their coefficients. So we'll have molecule ik, the coefficient for the first primitive Gaussian, times the coefficient for the second Gaussian. And then we have just the very simple term for the radial overlaps. So this Sij would be much more complicated if we had these angular momentum values, which we will have in future videos for sure. So we have the exponent. You do it with this math, sort of this object of the math class, which we imported up here. So math exponent minus q times big Q squared, which we just have as q2. And then it's times math.pi over p, and this is all raised to the 3/2. So yeah, this is literally the entire expression for the overlap of two s orbitals. This is just the radial components. If you had the p and d, like I said, you'd have much other stuff, or much more stuff over here. So basically just, I'll keep this here. Actually, no, I'm not. It looks sloppy. But yeah, you'd have a bunch of other stuff here. And then, of course, we need to return s here. So the function, this overlap function, returns s. This should pretty much be good. I'm almost positive there will be some bugs in here. So let's go ahead and start from the top and just rerun everything. So it looked pretty good. I guess let's just see if this works. Who knows if it will. Okay, so there's a list in the list here. You cannot do this with list and list, so I think what I should do is set this to be numpy array coordinates up here. So now these coordinates are numpy arrays. Only size 1 arrays can be converted to Python scalars. Yeah, so now I have to do this numpy dot here, I think. Oh, can't have the product like that. It's got to be like that. Okay, so something is wrong because these should be 1s here on the diagonal. So I guess let's go through with a fine-tooth comb and see what's going on here. So len molecule I, len molecule J, and then we have I here. So for K in this range, so IK A, JLA, that's right. Then we have P here, IK alpha, JL alpha, Sij. Oh, it's supposed to be plus equal because it's a summation. That's why. Yes. Okay, perfect. So here is our overlap matrix. Yes. I knew I was writing that right the first time. Yeah, so we're basically integrating, and we have to do the sum. So yeah, this is the overlap matrix in the STO3G basis for the 1s orbitals on hydrogen. This is sort of the Hartree Fock program beginning. So here I have this overlap matrix that we use here. In the next videos, we'll do the Fock matrix. But before this video ends, I do want to do the 631G basis. So I'll go ahead and just have this. I'll have all of this stuff here actually. So all of this is for the STO3G basis. So now what we're going to do is do the 631G basis for the 1s and 2s orbitals on hydrogen. So now we have a basis that is having the 2s orbitals. So we're going to start backwards like we did before. So I'm actually going to go ahead and put this overlap here. So let's make our molecule. It's hydrogen 1, 1s, hydrogen 1, 2s, and now we have hydrogen 2, 1s, and then hydrogen 2, 2s. Okay? So now we have 4 basis functions for our hydrogen, and up here for the STO3G basis, we only had 2 basis functions. So let's skate over here to the basis set exchange, and let's go to the 631G basis function set, which is here. Okay, click on hydrogen. Oh, I unclicked it. So I clicked on 631G, click on hydrogen, click on get basis set. Here it is. So here is the 1s, and then here is the 2s. Okay. So, and by the way, if it's not the 2s, I apologize. But I'm pretty sure it is the 2s. So we can now go ahead and put these in. So I have to make our primitive Gaussian object. So H1 PG1A, okay. I'll actually just go ahead and copy these because I think the 1s orbitals are pretty easy to do. So we will have that there, and then we'll have this for the next one. So I'm just copying these in, a little cumbersome, but it's a good exercise. Okay, and then we have to put in the contraction coefficients. Did I put this one in already? No. Okay, perfect. Now, we're going to have H1 from Gaussian 2A. Okay, so this is the 2s orbital. So it's just a single one. So now the contraction coefficient will be 1, right? For sure it will be 1. And we have now just this alpha value here of this. So it's only 1 because there's only one primitive Gaussian to describe the 2s orbital. Okay, so those are them there. Now let's copy it for hydrogen 2. Basically just call this 2 and change these, I guess, to 1.2. Okay. Now our molecule, now we need to make the basis functions. So we'll copy this here. Our basis functions will now be the same exact thing, except we have the 2s orbital at the end here. Okay. And, oh, no, that's not what we do, sorry. Got a little ahead of myself. So we have the 1s orbital on H1. Now we're going to have the 2s orbital on H1. So I started working forward, and you see I got stuck. I should have worked backwards the entire time. So yes, here is now our 2s orbital. It's just one primitive Gaussian. So now I have to have the 2s orbital on here. So this will be, yeah, just like this. So here I have the 1s orbital on H1. It's 3 primitive Gaussians according to the 631G basis coefficients. And now I also have the 2s orbital on H1, which is just a single component list here. And here's how I make my molecule. So let's go ahead, save this, and run it. Oh, I guess I need to do this overlap matrix here. Yes, so here is, I'm actually going to go ahead and print this. So print, we'll print the STO3G. So this is the STO3G results, is going to be this matrix here. So it's going to be for this molecule, and then we're basically going to overwrite everything. And we'll do the same thing for the 631G basis here. Okay, so I do want to just put a little space here. Okay, so this is the overlap matrix for the STO3G basis. This is the overlap matrix for the 631G basis, and you can see it's very nice. Works really well. So, and I guess in the next videos we might either go on to making the Fock matrix, computing these terms, or we might redo this sort of S matrix, the overlap matrix, but with the angular momentum terms in here. So yeah, thanks everybody. If you have any questions, please let me know, and I'll see you next time.